Let us wait 5 more minutes for others to join. If not, we will start the class. Thank you. Okay, let us start now. afternoon, everyone. So, this is Sayankara Karthika from the Department of Chemical Engineering, IIT Hyderabad. So, I'll be handling this live session. So, now we are into the week 9 of the Computational Fluid Dynamics course problem solving session. So, the course instructor is Professor Sreenivas Jayanti from the Department of Chemical Engineering, IIT Madras. And this problem solving session happens every week. There are two slots for the same. One is on Saturdays, handled by myself, and another one session is being held on Tuesday, handled by another TA. So mostly Saturdays 3 p.m. to 5 p.m. we have the session, unless otherwise informed priorly with any change if it is there. Now we'll start. So this is a computational fluid dynamics course, and which is a 12 weeks course. So we have almost covered till 8 weeks. The course lectures are handled by the professor, which is posted by the NPTEL. And while this problem solving session helps you in solving the problems for that particular week, so how I carry out is like I've just solved the assignment problems from the previous weeks and the practice problems for that particular week, so that you will get an idea to solve, and this will also help you guys in doing the exam, so you'll get an idea of how to solve the problems. So like in the first few weeks, the course is about calculation of flow in a rectangular duct and triangular duct, and afterwards we dealt with derivation of the equations governing the fluid flow, and for that we have seen the equations for incompressible flow and boundary conditions. After that we have seen the basic concepts in CFD like finite difference approach, and this finite difference approach was what it was dealt in the rectangular duct problem, and in triangular duct we have seen the finite volume method also. After that we have seen the consistency, stability and convergence criteria when we are dealing with the discretization of the geometry under consideration. So like how the problem can be uh, solved to get a solution. Like the solution should be consistent and it should be stable, and we should get a converged solution. After that it was about solution for Navier-Stokes equations for compressible flows and incompressible flows. In the last week session we saw the practice problem for the incompressible flows, while in this week we'll be seeing how to solve the Navier-Stokes equation for incompressible flows, and followed by that we'll also see solution of linear algebraic equations using basic methods. So now we'll start the session. Oh, sorry. So this week it is mostly about solution of Navier-Stokes equations using compressible, incompressible flows, and then so it will be mostly like all the concepts will be brushed off from the theory class. I mean, so that the problems are comparatively easier this week than what we have seen in the previous weeks. So we'll start the session. So the first problem, the question is about which of the following statements is correct about incompressible flows. The first statement, it is mentioning that most liquid flows are incompressible. Second one, flow of air can be incompressible if the fluid flow is sufficiently high. So the question is about this particular figure. So which of the following statements is correct about incompressible flows? So first one, most of the liquid flows are incompressible. Second one, flow of air can be incompressible if the fluid flow speed is sufficiently high. So in the last week's class itself, we have seen how to connect the compressibility with the fluid flow speed. It is obtained using the Mach number. Mach number is nothing but the local flow velocity by the speed of sound in that particular medium. So if Mach number is high, we call it compressible. If Mach number is less, we call it incompressible. So imagine if the flow velocity is very high, we would get the Mach number very high. If the Mach number is very high, we would be defining it as compressible. So the second statement is false. Flow of air can be incompressible if the flow speed is sufficiently high is a false statement. What is correct? Flow of air can be compressible if the flow speed is sufficiently high. So our flow of air can be incompressible if the flow speed is sufficiently low. And the first statement, coming to that, most liquid flows are incompressible. That also we cannot say, like similar to the Second statement, the fluid flow, that is the liquid flow, can be incompressible or compressible. Here we are not dealing about the fluid type. Here the compressibility denotes the flow, like not the fluid behavior, like fluid type. Fluid type we call it like liquid fluids or incompressible fluids. But here the question is about compressibility of the flow. So the both the statements like can be looked at in a way that the first statement, it is mentioning that most liquid flows are incompressible, like almost it would be incompressible. Like sometimes it can be adjusted according to our need, but in the most scenarios, the liquid flows would be incompressible. Like we cannot change the density variation would not be very high. Like if even if the fluid flow velocity is very high, there would not be that variation, because again the Mach number would be less than 0.3. So we call it incompressible fluid flows even when we are dealing with the liquids. The key to that is most liquid flows. It is not that all the liquid flows are incompressible. If it is all the liquid flows, we cannot say that. It can be changed in certain scenarios. Certain cases it can be false also. So here the keyword is most liquid flows are incompressible. This is true. Which is false? All liquid flows are incompressible. If it had been given like that, the statement would have been a false one. So which of the following statement is correct about incompressible flows? Most liquid flows are incompressible is a right statement. Whereas the second statement, flow of air can be incompressible if the fluid flow speed is sufficiently high. Like the speed of air, even if it is high, it would be compressible. If it is low, it can be called incompressible. Similar to that, the liquid flow speed is not comparable with the fluid, I mean gas speed, because like the Mach number is the ratio of the fluid flow speed to the speed of sound in that particular medium. So that would be always, or in most cases, it would be less than 0.3 for the liquid flows. Therefore, we can say that most liquid flows are incompressible. So coming to the options, option A it is 1, option B it is 2, option C it is 1 and 2, option D it is neither 1 nor 2. So obviously second statement is a false statement. Therefore the only right statement is most liquid flows are incompressible. So right answer to this particular question is option A is the right answer. That is most liquid flows are incompressible. We'll go to question 2. Okay. While all flows are compressible, fluid flows are treated as incompressible when Mach number is smaller than 0.3. Mach number is the ratio of U by C, where U is the local flow velocity and C is the speed of sound in that medium. If velocity is high, Mach number would be high. If Mach number is high, it is not compressible. It is not incompressible. It is compressible. While all flows are compressible, flows are usually treated as being incompressible when Mach number is smaller than 0.3. So, Mach number is the ratio of U by C, where U is the local flow velocity and C is the speed of the sound in the medium. If velocity is high, Mach number will be high. If Mach number is high, the flow is compressible flows. So, velocity should be low for us to get an incompressible fluid flow domain. While the liquid flows, most cases it can be considered as incompressible fluid flow. Now we have moved on to question 2. In question 2, it is asked that which of the following is or are among the difficulties encountered in the solution of incompressible flows. First one, coupled equations. Second one, non-linearity of governing equations. Third one, determination of pressure. So what is asked in the question? we are given three uh, options, and of that we have to choose which are the difficulties encountered while we are going with the solution of incompressible fluid flows. Let us now deal with it. So the first option is coupled equations. So for a fluid flow equations, what are the equations we would be solving? We would be solving for the continuity equations and momentum conservation equations, or the Navier-Stokes equations. So in Navier-Stokes equations, there is a pressure and there is a velocity. So pressure velocity coupling exists. And since it is a incompressible flows, density would also be included in that, and we would not be taking it out separate. So sorry, incompressible one, density would be assumed as constant, and it can be taken out separately. Like unlike in compressible flows where density would be varying too, and therefore we cannot eliminate it from the equation. Whereas here it can be eliminated. But apart from that, we have the pressure variation along the system, and we have velocity variation, which is accounted in the momentum conservation equations. So pressure velocity coupling is there, which is like very difficult to get it from the system, like system of equations. So coupled equations poses one difficulty. Second one, non-linearity of governing equations. If you remember in the Navier-Stokes equations or the momentum conservation equations, we have terms including uv and u square in the x domain and uv and v square in the y domain for the two-dimensional problems. So these are not linear. So non-linearity of governing equations is one such difficulty which is encountered in the solution of incompressible flows. And third one is determination of pressure. So while we are dealing with the compressible flow system, we have seen that how were we obtaining the pressure? We were obtaining the pressure from the equation of state. While here in incompressible flows, that is not possible. Pressure is part of a equation. So here determination of pressure is a difficulty. Whereas in the compressible flow systems, determination of pressure was not a difficulty because we got the pressure from the equation of state. But for incompressible flow system, we need to understand that determination of pressure is also equally difficult. So from these options, if we see, all three are equally are among the difficulties encountered while solving the incompressible flows. Here we need to understand we are solving for the incompressible flow solutions. So all three options are right, and let us now look at the choices. And the first one, option A, it is 1 and 2. 1 and 2 are right, but again here the third option is left out. Whereas in second option B, we have 2 and 3. Again first one is left out, and in option C we have got 1 and 3, where second option is left out. Whereas in the option D, we have all three options, that is 1, 2 and 3 is included. So the correct answer to this problem is option D. So how is that? We have continuity equations, dou u by dou x plus dou v by dou y is equal to 0. For a two-dimensional problem, here we are looking at the equations. And the thing is, here if you remember, there would be a presence of rho in the continuity equations for the compressible flows. But here, since we are dealing with incompressible flows, we can assume the density to be constant and it can be taken out of the equation. And the second one, we have got dou u by dou t plus dou u square by dou x plus dou u v by dou y is equal to minus 1 by rho dou p by dou x mu by rho dou square u by dou x square plus dou square u by dou y square. Similarly, for the y direction, we have got dou v by dou t plus dou rho u v by dou x plus dou rho v square by dou y is equal to minus 1 by rho dou p by dou y plus mu by rho dou square v by dou x square plus dou square v by dou y square. So this is what I was saying. We have the presence of velocity as well as pressure in the equation, which is both of them are varying. So pressure is also varying and velocity is also varying. So pressure and velocity is coupled in this particular equations. So that is one problem. And second one is, here we have u square, here we have uv. There is a non-linearity existing in this particular case. So non-linearity of the governing equation is another issue which we are encountering. And third one is determination of pressure. So since there is a coupling between pressure and velocity, we are determination of pressure is also an equally difficult problem. So all three options are right in terms of the difficulty. Like coupling, coupling of the terms of the variables, and nonlinearity of the governing equations, and determination of pressure. All three are equally difficult while we are dealing with incompressible fluid flow domain. If it is compressible, determination of pressure is not an issue because we can get it from the equation of state. So during the exam you might be having all the topics together. Even if it is in weekly problems, one week you are dealing with compressible flows and the next week you are dealing with incompressible flows, so that it was easier to solve the same in terms of how can I say, like one week you would be focusing only on compressible flow, so you would remember determination of pressure is from the equation of state, and in the next week you are dealing with the incompressible fluid flows, so you would remember determination of pressure is a difficulty. Whereas in the exams it would be coupled and combined together, the entire course would be, entire syllabus would be covered, so there it might become confusing, so just be clear in that. So that's it. So now let us move on to question 3. Consider the steady incompressible flow through the contraction section of a circular pipe shown schematically in figure 8.1. For this flow, which of the following can be neglected? So this is the figure. What is given? There is a steady incompressible flow through the contraction section of the circular pipe as shown in figure 8.1. So in this case, which of the following can be neglected? So let us first understand what is given in this problem and then we'll see the options. The first one, it is mentioned steady state problem. So, sorry, I just bit my tongue. Sorry. So here it is mentioned that the flow is a steady state problem. So steady flow is happening. And second one, it is incompressible flow through the contraction section. That is obviously mentioned. So here it is a steady and incompressible flows. So if we are dealing with incompressible flow, what should come in our mind? Incompressible flows, there is no major change in the density, and therefore it can be neglected. So let us now see which can be neglected. First one, pressure variation in the flow direction, and second one, density variation in the flow direction. Second one is as we discussed, whereas the first one, it is pressure variation. Pressure variation cannot be neglected. Like if imagine that you are dealing with the pipe flow, the majority of the flow happens because of the pressure difference, so pressure variation cannot be neglected when we are dealing with the incompressible flows. And but in since it is mentioned that the flow is incompressible fluid flow domain, we can ignore the density variations because the density variation would be very minor, like those changes are very less. So density variation in the flow direction can be neglected. So on looking at the options, we have option A 1, option B 2, option C 1 and 2, option D neither 1 nor 2. So as we all know that second option is the right. So option A is false, option B is right, option C and D are again false because we are dealing with incompressible fluid flow problem. There is pressure variation existing, whereas density variation can be neglected in the flow direction. Density variation in the flow direction can be neglected, but for the pressure variation we cannot neglect it. Like pressure variation is equally important considering it is a steady incompressible fluid flow problem. We need to account for the pressure variation. Imagine then if even if that goes to zero, there would not be only velocity terms remaining in the governing equation. So that's it. Yeah, like here it is mentioned along the flow direction, so we cannot neglect the pressure variation along the flow direction. That is important. In like when we are dealing with any system or any variables, just imagine in what direction they are asking, and that would give you an idea whether it would be ignored or it should be there. In our case, it is like density variation in the flow direction can be neglected and pressure variation in the flow direction needs to be accounted. Now let us move on to question 4. In question 4, it is asked that if the flow in figure 8.1 is unsteady, axisymmetric and viscous, then how many partial differential equations need to be solved to get the flow field? So what is asked? So the figure is the same, like here again we are dealing with the figure 8.1, but here it is an unsteady problem and axisymmetric problem and viscous problem. So when you are dealing with a circular cross section, you can see that it is a three-dimensional problem, but we need to look at what is given. The three keywords are unsteady problem. So like the velocity would be varying with time. That can be accounted in the momentum conservation equations. So that would not reduce any equation. And axisymmetric. So since it is given axisymmetric, we can take the problem in a two-dimensional domain. Axisymmetric is nothing but along the axis it is symmetry in both the directions. So rather than solving for three-dimensional problem, we can account it in a two-dimensional problem and then get the solution, and then we can just say that it is like a replica of the other direction. And then we have, it is an incompressible fluid flow problem, so we need not solve for the energy equations. So if we look at, we have one continuity equations, and since it is a circular cross-sectional pipe, we should have three momentum conservation equations. But in this particular case, it is mentioned that the flow domain is axisymmetric. Therefore, we are reducing it to a two-dimensional problem. So if we reduce it to a two-dimensional problem, we have only two momentum conservation equations along x and y directions. Therefore, on the whole, we have three partial differential equations, one continuity equations and two momentum conservation equations. So we have three equations. Let us look at the options. Option A, it is 5, false. Option B, it is 4, which is again false. Option C, it is 3, which is again false. Option D, it is 2. Sorry, option C, 3, it is right. I am sorry. Option C, it is 3 is the right answer. And option D, it is mentioned 2, which is a wrong answer. So right answer is option C is the right answer, where we are solving for three partial differential equations. Why is it? We are here, it is mentioned unsteady, axisymmetric and viscous problems. So because we are considering axisymmetric problems, we are neglecting one direction and therefore we are left with 3 minus 1 direction. So we have two momentum conservation equations and one continuity equation. On that basis, we have three partial differential equations. So C, option C, 3 is the right answer. We'll now look at question 5. Question 5. For the steady axisymmetric incompressible laminar flow case shown in figure 8.1, which of the following statements is true about the stream function vorticity method? For the steady axisymmetric incompressible laminar flow case shown in figure 8.1, which of the following statements is true about the axisymmetric which of the following is true about the stream function vorticity method? Option 1, it cannot be used because the flow is laminar. Option 2, it cannot be used because the flow is 3D. And third, it cannot be used because the method can be only used for Cartesian coordinate system. Of these three statements, there is one statement which is logically or technically right when it is concerned with the stream function vorticity approach, but it is false with regards to figure 8.1. I'll give you guys a minute, so in that time just please understand and see which of the following is the right statement irrespective of this problem, and which of the following statement is sorry which of the following statement is wrong irrespective of the problem, and which of the following statements is right when it is mentioned outside of the context of this particular figure. So just take a minute and analyze and bring out the key points in stream function vorticity approach, and we'll discuss. Guys, give me a minute. Actually, there is something I need to take care. Just give me a minute. Yeah, I am back now. So now we'll discuss. There was some small thing I needed to take, like small work which was needed to be taken care. So I just left for that. So we'll just now look at the options and identify which of the following are right, irrespective of the problem, or which of the following is wrong, irrespective of the problem, and which of the following can be right if it can be used in another context. So the first one, it is like it cannot be used because the flow is laminar. Here we are dealing with stream function vorticity approach. In stream function vorticity approach, we introduce two other variables, stream function and vorticity, and eliminate the pressure term. And it is applicable only for transient system and 2D systems. So you need to remember that it is applicable for transient and 2D systems, or pseudo steady state systems, we can call it, and therefore it is applicable for only 2D systems. So we'll just see the first option. Option, it cannot be used because the flow is laminar. It is false because it can be used if the flow is laminar. There is no restriction to that particular case. So first one is false. Second one, it cannot be used because the flow is 3D. First of all, the flow is 3D, but we are dealing with an axisymmetric system. So here we can reduce it to a two-dimensional problem. So it can be used in this particular case. Because it is mentioned axisymmetric, we are dealing with only two-dimensional case, and therefore, since although we are using stream function vorticity approach in this problem, we can reduce it to our desirable approach because it is mentioned axisymmetric problem. So second statement is again false because it can be used in this system. And third one, it cannot be used because the method can be only used for Cartesian coordinate system. Again, it is false. Like here, we are again reducing it to a like two-dimensional problem, and therefore there is no issue in that. So let us look at the option. Three statements are again true. Therefore, option A 1, option B 2, option C 3. All three options are wrong. Option D, it is mentioned none of the three is correct. Therefore, the right answer is option D. None of the three is correct. I hope it is clear because it is mentioned that axisymmetric problem, we need not worry about that, and therefore it can be used anywhere. Like although stream function vorticity approach is limited to transient 2D problem. So steady state 2D problems, it can be used in this particular case also. So none of the three is correct is the right answer. We'll go to question. Okay. We'll go to question 6. Okay. Before that, just a quick explanation. For 2D incompressible flows, it is possible to recast the new Navier-Stokes equations in an alternative forms in terms of the stream function and the vorticity. In many applications, the stream function vorticity from the Navier-Stokes equation provides better insight in the physical mechanisms driving the flow than the primitive variable formulations in terms of U, V, and P. So what is mentioned, it is possible to recast the Navier-Stokes equation in an alternative forms in terms of stream function and the vorticity. So we are just recasting the Navier-Stokes equations into some other forms in terms of the stream function and the vorticity variables for two-dimensional incompressible problems. And in many applications, stream function vorticity approach or stream function vorticity form of the Navier-Stokes equations, it provides better understanding into the physical mechanisms than what it is driving the flow than how like uh, compared to the traditional method of writing it in the form of u, v and rho, sorry, u, v and p, because rho it would not be coming in incompressible flow problems. And third one, it is stream function and vorticity formulation is also useful for numerical work since it avoids some problems resulting from the discretization of continuity equations. So, like stream function and vorticity formulation also has an additional advantage while solving it using numerical approach because it avoids some problems resulting from the discretization of the continuity equation in the traditional method of representation by using U, V, and P. I hope it is clear now. We'll go to question 6. In question 6, it is asked that for the steady axisymmetric incompressible laminar flow case shown in figure 8.1, which of the following statements is true about the artificial compressibility method? So, actually, I hope by now you know there are four methods explained in the lecture for solution of Navier-Stokes equations for incompressible fluid flow problems. So, the first one, irrespective of the order, we have artificial compressibility approach where we introduce an additional like P star in order to convert it into a similar term like compressibility, so compressible fluid flow domain. And second, we have stream function vorticity approach, which we have seen in the last slide. And third is pressure correction method and pressure equation method. So, I'm sorry. So what was I saying? Like four approaches, and in that artificial compressibility method, the question is about that. So similar to how it was about stream function vorticity approach, here we are just given. Here the question is about artificial compressibility method, and we are given three statements. And the first statement, it is about it cannot be used because the flow is laminar. Again, it is false because it can be used in this case as well. And second one, it cannot be used because the flow is 3D. Again, it is false. Because only stream function vorticity approach has a limitation for 3D. And again here, however, we are not dealing with a three-dimensional problem because the axisymmetric limitation is existing here as well. So it can be used even if there is a limitation to 3D 3D problem. Here, however, we are dealing only with the two-dimensional problem, so it can be used. Third one, it cannot be used because the flow is steady. So the steady state approach, if it had been given in the stream function vorticity method, there it is true, because stream function vorticity approach cannot be used for the steady state problems. However, artificial compressibility method has no such restrictions, and therefore we can use it. So all three statements are basically false, because the first one, it cannot be used because flow is laminar, false because it can be used. Second one, it cannot be used because the flow is 3D, again it is false because it can be used, and the flow we are dealing with, it's not a three-dimensional problem, because how we have reduced it to a two-dimensional problem because the condition of axisymmetric is mentioned. And third statement, it is about it cannot be used because the flow is steady. Again, this is false because there is a limitation of steady state only for the art like stream function vorticity method. There is no restriction for the artificial compressibility method. So all three statements are wrong. Let us now look at the options. A1, which is false, B2, which is false, C3, again it is false. Option D, none of the three is correct. Again, in this particular question, the right answer is option D. That is, none of the three is correct. I hope it is clear now. Last question, it was about stream function vorticity method, but in this question it is about artificial compressibility method. Only that difference is there. And so last options we have eliminated on the basis of considering stream function vorticity approach. Stream function vorticity approach has a limitation for steady state and three-dimensional problems, whereas in this particular artificial compressibility method there is no limitation for steady state. Therefore, we can in fact use it, and therefore the none of the three is correct is the right answer. In fact, what it is it can be used for steady state problems. Because this additional term we are introducing would go in terms of variation with time only. Yes, that's it. Now we'll go to like artificial compressibility method can be used for three-dimensional problem. So the second statement itself is false. It cannot be used because the flow is 3D is false, because artificial compressibility method can be used for three-dimensional problems. I would like to have an answer, like just answer it whenever it is possible. Is my voice clear and audible, or are there any disturbances? And the second one is, am I going too fast, or is the speed sufficient? Like while pronouncing certain words, are you able to figure out what I am saying, or if there are any difficulties? Like, so if you guys can just answer these, I think it would be helpful for me and you people as well, because I can modify it based on the feedback. That's it. Now we'll go to question 7. Which of the following methods can be used for the flow shown in figure 8.1? So again we are dealing only with 8.1. 8.1 we need to understand what it is. It is incompressible flow through contraction in a pipe of circular cross section. So we have a circular cross sectional pipe and we have incompressible fluid flow happening through that. Contraction, like there is a contraction section in a pipe of circular cross section. So which of the following methods can be used? So incompressible fluid flow, if it is incompressible flow, what method can be used? We can use artificial compressibility method, we can use stream function vorticity approach, we can use pressure equation method and pressure correction method. So if we are dealing directly with that, we cannot use stream function vorticity approach unless until it is mentioned axisymmetric, because it is limited to two-dimensional problems. Whereas if the flow had been compressible, what methods were available? We had two methods, McCormack scheme and beam warming scheme. Like McCormack scheme was for explicit method and beam warming scheme was an implicit method. So on that basis, here we have incompressible flow. We have therefore four options, and in that we have eliminated three options. Like stream function vorticity is eliminated. So we'll look at the options and see which is a suitable one. The first one is McCormack method. It is false because it is a method used in getting solutions for the compressible flow. And second one is pressure equation approach. It is right. And third one is pressure correction approach. Again, it is right. Therefore, 2 and 3 are the right ones. Okay, we just find out from the options given. Option A, it is 1 and 2. 1 is false. Option B, 2 and 3, it is right because pressure equation approach and pressure correction approach are the ones which are used for getting the solution for incompressible fluid flow domain problems. And option C, it is 1 and 3. Again, 1 is present, which is false because it is a McCormack method. McCormack method is an explicit scheme used in getting solutions for the compressible fluid flow problems. And last is option D, 1, 2 and 3. 1 is again included, which is false because McCormack method is not used for compressible. It is not used for incompressible method. In the figure 8.1, it is clearly mentioned that it is an incompressible flow through contraction in a pipe of circular cross section. So, like, answer to this is option B, that is 2 and 3. If you're not very thorough with the concept, sometimes what we do is we eliminate the option based on some other patterns or something. On that option, on that basis, the first one would be eliminated, would be option B, because in all other options, like, we have one. Therefore, sometimes we do this silly logical reasoning and we eliminate B, but we should not do that. This is a right option here. So therefore you can see that we cannot eliminate the options from the MCQs based on some patterns or something, because chances are there that would lead us to a wrong option. Yeah, like, because here it is like one is repeated everywhere, so we might think McCormack method is some answer if we do not know the concept. I am saying in that case, like, sometimes we do that when we don't have an idea about what it is, but we want to attempt it or we want to give it a try. So that's it. But here in this, it is pressure equation approach and pressure correction approach are the ones which are used for incompressible flow through pipe. So option 2 and 3 are right, which is correctly provided in option B. Therefore option B is the right answer. We'll go to question 8. Okay, methods for solving incompressible fluid flow. First one is artificial compressibility method. Second one, stream function vorticity approach. Third one, pressure equation approach. And fourth is pressure correction method. So all these methods are well explained in the course lectures by the professor. So you can, like, you must have understood that and read that for your examination, because that would be what you are dealing with. So yeah, we'll now move on to question 9, I guess. Okay, question 8. The pressure correction approach cannot be used for time dependent flows, three-dimensional flows, viscous flows, none of the above. So pressure correction approach is an approach for getting solution for the incompressible Navier-Stokes problem. So we previously have seen 4 approaches were there, and pressure correction is one such approach. And in this question, it is asked about the limitations encountered while solving a problem using pressure correction, if there are any. Like, the first one is time dependent flows. It is false because pressure correction approach can be used for time dependent flows as well. Like in what is it? Stream time function vorticity approach also, we were only dealing with the transient problems. We were not dealing with the steady problems. Similar to that, pressure correction approach. Actually, pressure correction approach, it is like an hardcore chemical engineering problem solution. So it can be used for time dependent flows as well. Very popular technique for incompressible fluid flow domain. It is very useful for transient three-dimensional problems, and therefore time dependent problems, that is the solution is varying with respect to time. It can be used. Pressure correction approach can be used. However, the question is about cannot be used. So option A is false. Option B, three-dimensional flows. Again, I've said like pressure correction approach is a hardcore chemical engineering approach for getting solutions. I mean, not hardcore chemical engineering approach, I should not say that. But pressure correction approach is a very popular technique among the hardcore chemical engineering problems, which are mainly dealt with three-dimensional problems, three-dimensional flows. Therefore, second option is also false. Option C, it is viscous flows. Again, this is false because there are many problems where we deal with viscosity variation. So yeah, it is false again. Whereas option D, none of the above is the right answer, because we are all three options are wrong. Therefore, the only options left is none of the above. Option D. So yeah, we'll go to question 9. Okay, before that, just a brief explanation. Pressure correction method is a class of methods used in computational fluid dynamics for numerically solving the Navier-Stokes equation, normally for incompressible flows. So what is it? It is a class of methods used in CFD for numerically solving Navier-Stokes equations, normally for incompressible methods. So it is a method used for getting solutions for the Navier-Stokes equation in incompressible flow problems. So what are the steps involved? So initially we guess P star, U star, V star, and solve discretized X momentum equation for U star and Y momentum equation for V star. And after that we solve pressure correction equations for P dash, and then we calculate velocity corrections U dash and V dash, and calculate other scalars. After that, we update the initial PUV and return to the first step if it is not converged. Like, we first have a guess of P star, U star, V star, and using that we solve the discretized X momentum equation and Y momentum equation and pressure correction equations. We get P star. After that, we calculate the velocity correction U star and V star. So after that, we calculate the other scalars and then get updated P, U and V, that is pressure and velocity vectors U and V. And if it is not converged, we return to the original step and follow the steps again. So here nowhere it is mentioned that it cannot be used for three-dimensional problems or time-dependent problems. So all three options given in that particular question were wrong. So we went with none of the above. So now we go to question 9. It is a simple question, I must say. So the full form of the simple method, that is SIMPLE, is option A, steady implicit method for pressure linked equation. Option B, scheme for incompressible pressure linearized equations. Option C, semi implicit method for pressure linked equations. And option D, it is steady incompressible method for pressure linked equations. I'll just make a small correction over here. This L should have been capital. So SIMPLE. So it is semi-implicit method for pressure linked equation. That is the right answer. So first one, it is steady implicit method for pressure linked equation, which is false because it is a semi-implicit method. Again, option B, it is scheme, which is false. Incompressible, false. Pressure linearized equation, option B, is completely false. Whereas option C, it is semi-implicit method for pressure linked equations. This is the right answer. Option D, it is about steady incompressible method for pressure linked equation. Steady incompressible. Steady is false, again incompressible is false. Only last three are right. So answer is simple semi-implicit method for pressure linked equation. Option C is the right answer. I hope it is clear now. We will go to question 10. In question 10, a staggered grid system is used. Option A, to enable treatment of flow domain of irregular shape. Option B, to simplify grid generation. Option C, to eliminate checkerboard oscillation in pressure. To option D, to overcome stability problem. So it is about a staggered grid system. Why it is used? Option A, to enable treatment of flow domain of irregular shape. That is false because it is not used for that purpose. To like for irregular shape it is not like that. And option B, to simplify grid generation, again it is false because we are not using staggered grid approach to get the grid, simplify the grid generation. Option C, to eliminate pressure oscillation, checkerboard oscillation and pressure. That is the right answer because while we are dealing with pressure equation approach, like sometimes we are dealing with dou p by dou x, that is variation of pressure along that direction, and we are dealing with adjacent grids, right? Sometimes like if you are using a center difference approach, what you would be doing, use take the values from this cell and the next cell, I mean next to next cell, that is pi plus 1j minus pi minus 1j by 2 delta x. If it is there, we might have the same pressure and it becomes zero. So there are like fluctuations would be there in the final solutions, and to get rid of that we use the staggered grid approach. The staggered grid approach is nothing but we calculate the values of scalar at particular domain and calculate the values of vectors like u and v at different domains. Mostly like we calculate the values of scalars in the cell center or in the cell grid points, whereas calculate the values of the u and v variables velocity vectors at the center of faces or something. To get a more clear idea, like staggered grid is that we calculate the pressure at the center of the like pressure calculation is at this pressure, temperature, everything, pressure and scalars at the center of the cell, whereas we calculate the values v star at here and u star at the center of the faces. This is cell center and this is face center. So you can have this picture is taken from this particular journal. Numerical investigation of complete evaporation process in Z porous evaporator using staggered and non-staggered grid arrangements. International Journal of Thermal Sciences. Here you can use the DOI also. But if it is a non-staggered, what is the difference? We have the pressure and velocity. That is, rather than saying pressure and velocity, we can say the scalars and vectors are calculated at the same points. So the chances are there to get fluctuations in the final solution because it might become zero and we get instability. Therefore, to eliminate the checkerboard oscillations in pressure, we use staggered grid systems. The chances for pressure to become zero is there if we use the non-staggered grid. So we go for staggered grid system to eliminate the checkerboard oscillations problem. Therefore, we use staggered grid. So right answer to this problem is option C is the right answer. So answer is option C. So we have just seen 10 problems. Let us now take a 5 minutes break because time now is 4 o'clock. We can have a 5 minutes break and then we'll start the session. So we can start now, I guess. What is the time? Yes, we can start now. 5 minutes has passed. So now we are into question 11. In question 11, it is asked that consider the flow situation shown in figure 8.1. For which of the cases below will the flow likely to be incompressible? So it is a question similar to what we have seen previously. Like question is asked in a different manner, but it is the same. Like conceptually, it is the same. So what is asked? Which of the flow is likely to be incompressible? Which of the cases below will likely to be incompressible? So the first one, when the gas flowing through is nearly inviscid. Second, when the gas flow velocity is extremely low. So what is asked? When the gas flowing through is nearly inviscid. And second option, it is when the gas flow velocity is extremely low. When will the flow be incompressible? Hmm. Okay, so it is about, so if you remember in the question 8.1, for which of the cases below will the flow likely to be incompressible? Option 1, when the flow is nearly inviscid, and the second one is when the flow is extremely low. So since it is an compressible flow situation, so it is already mentioned that the flow is incompressible. So under what condition it can be below flow, for which of the cases below will the flow likely to be incompressible? So already it is mentioned that it's an incompressible flow. So if the gas flow velocity is extremely low, in general case it is an incompressible, but here since it is already mentioned, the answer is neither one nor two. So when gas flow through is nearly inviscid or when gas flow is extremely low, both are wrong actually. You wish to compute the velocity and pressure variation, or else just give me a minute, like just give me a moment. I just made a mistake in the previous question. So the question is that, will consider the flow situation for which of the cases below will the flow likely to be incompressible. Okay. So this is figure 1 actually. So I just made a wrong figure, so therefore I am rectifying it. Like in the previous flow it was about uh, contracting section, while in this figure it is about diverging section. So I have taken from two different sources the questions, therefore the confusion is created. So since it is after reading the question I realized my mistake, and now I am just giving you guys a corrected version. So like forget the question 11 which we discussed previously. It is a false because it is a contracting section. So velocity like is uh there the question is a different one. Like velocity can be low as well. But here the question is different because you velocity is inversely proportional to area, if you guys remember. So if the area is high, velocity would be low. If the area is low, velocity would be high. So like technically here the velocity is low. So the flow is independent of this. So for which of the cases below will the flow likely to be incompressible? So it is mentioned that incompressible flow through a diverging section expansion. So it is fluid is getting expanded. So like when the gas flow is nearly inviscid, false, and when gas flow is extremely low, again it is false, because it is like both the statements are wrong with respect to this context, because here we are like um ex- just give me a moment, I'll just give a proper explanation for this question, although it is simple, I just got a bit confused. Okay, so here we are having a diverging section expansion. So the velocity is with respect to the expanding section, there is like a change in velocity. So here incompressible flow through a diverging section expansion, meaning that the gas velocity is fluctuating over here, so that when the velocity is nearly inviscid, we say it like it doesn't affect. And in the second statement as well, when gas flow velocity is extremely low, again here it is velocity is varying, like here velocity is more, and here velocity is more, and here velocity is becoming less, and it is remaining the same. So incompressible flow through a diverging section, velocity is varying over here. So a gas flow velocity is extremely low, is not like here if you can see that velocity is high and it is getting reduced. So that thing, when it is there, like here we cannot say that in which of the cases will the flow likely to be incompressible, we cannot just determine with that. We need to get an exact value, and then we need to determine the value of Mach number as well. So it is like which of the following is cases will the flow likely to be incompressible? Both are wrong, neither one nor two. When gas flowing through is nearly inviscid, or when gas flow is extremely low, because both of them are wrong. So neither one nor two. Which of the cases will the flow likely to be incompressible? Like if it is a gas flow, chances of it becoming compressible is also there. That's why. Okay, we'll now just look at question 12. Why it is not moving? Hmm. I think I just wasted some time now, so we have to hurry up. Okay, in question 12, it is about you wish to compute the velocity and pressure variation for the flow in figure. Okay, it is 1. Figure 1 is nothing but which we have seen in the last slide. That is nothing but a diverging section. Sorry. Yeah, it was a diverging section, I guess. Yeah, a diverging section expansion. So you wish to compute the velocity and pressure variation for the flow situation in figure 1. Flow is two-dimensional. So it is a two-dimensional problem. Upstream and downstream ducts are extended on both sides of the expansion joint as shown in the figure. So upstream duct and downstream duct are both extended on both sides of the expansion joint. Which of the following statements is correct? Inlet flow velocity profile will not have any bearing on the flow in the expansion, and therefore it can be taken as uniform. Second one, outlet velocity profile will not have any bearing on the flow, and therefore it can be taken as uniform. So first one, what is given, we are dealing with the expansion joint, and in both the upstream and downstream ducts it is mentioned that it can be extended on both sides of the expansion joint. Therefore, which of the following statement is right? So one statement is about inlet velocity profile, and second statement it is about outlet velocity profile. So what does first statement here mention? It is mentioning that inlet velocity profile will not have inlet velocity profile will not have any bearing on the flow in the expansion. So in most cases, inlet velocity can be taken as an uniform because here it is coming from some other source. Therefore, it is uniform. There is no change to the inlet velocity profile. Therefore, the first statement is a right statement. Whereas in the second statement, it is mentioned that the outlet velocity profile will not have any bearing on the flow and therefore it can be taken as uniform. That is false because here we are dealing with the expansion section. The flow is expanding over, it is diverging. Therefore, the velocity is changing with respect to position as well as time. Therefore, we cannot say that outlet velocity profile will not have any bearing on the flow and therefore it can be taken as a uniform, which is a false statement. Outlet velocity profile cannot be taken as a uniform because it will have some bearing on the flow. Therefore, it is a false statement. So, first statement is right, second statement is false. According to that, we have A1, it is right. B2 only, it is false. C1 and 2, it is again false because it is inclusion of option 2. D, neither 1 nor 2. Again, it is like false because 1 is true. Inlet velocity profile here can be taken as a uniform, whereas outlet velocity profile cannot be taken as a uniform because there is a change in velocity. This is what we have seen in the previous slide also, where there was a change in velocity field, like velocity values were decreasing, and therefore it was not taken as an incompressible flow because the velocity were changing with respect to the area, because it is like there is a almost 10% change if you take the area is changing 10%. Therefore, it was a false, and therefore accordingly the same thing, outlet velocity profile will not have any bearing on the flow is a false statement because it will have, and therefore the right answer is option A. We'll now go to question 13. In question 13, it is asked that if the flow in figure 1 is a steady, viscous, two-dimensional and does not involve any external heat transfer, then how many partial differential equations do we need to solve to get the velocity field? So figure 1 is that diverging section. So if the flow is a steady state problem and viscous problem, two-dimensional problem. So, and does not involve any heat transfer, so we need not solve for the energy equation. So how many partial differential equations do we need to solve? We have 4 equations when we consider the continuity equations and the Navier-Stokes equation in 3 dimension. But it is clearly mentioned in this problem that the flow is a two-dimensional problem. Therefore, the number of PDEs need to be solved is just 2. I mean not 2, like 3, because we have 1 continuity equations and 2 momentum conservation equations. So on the whole we have 3 equations. So on the basis of the options, we have option A 5, option B 4, option C 3, option D 2. So right answer is option C 3. We'll go to question 14. It is similar to the problem we have seen in the previous slide. If the flow in figure 1 is isothermal, steady, viscous, two-dimensional, which of the following statement is true about using stream function vorticity method? So what is mentioned? It is an isothermal problem, steady state problem, viscous problem, two-dimensional problem, and we are using stream function vorticity approach. Stream function vorticity approach, it has a limitation for two-dimensional problem, and it is a transient problem. So the first statement is it cannot be used because the flow is laminar. It is false because it can be used for laminar flow problems. And second, it cannot be used because the geometry cannot be fitted in rectangular grid. Again, it is false because it can be done. Because it is a two-dimensional problem, it can be easily fitted. It cannot be used because the boundary condition for stream function of the wall is not unique, which is not true. So all three statements are false. Coming to the options, we have option A1. Which of the following statement is true is the question. So option A is false. Option B 2 is again false. Option C 3 is again false. Option D none of the three is correct is the right answer. Option D is the right answer. Option D is the right answer. Now we have question 15. In question 15, it is about pressure correction approach can be used for which of the following. So remember, the same question was asked in a different way in the previous few questions back. So in that it was about it cannot be used for which of the following. So that there, I think it will be eliminated almost all the options, I guess. So here it is about it can be used for which of the following. First one, it is time dependent flows. Second one, three dimensional flows. Third one, viscous flows. As I have mentioned previously also, pressure correction approach is like used in almost all the core chemical engineering problems concerning three dimensional flows and time dependent flows. So on that basis, like it can be used for time dependent flows, and similarly it can be used for three dimensional flows, and it can be used for viscous flows as well. So all three are right here. Like in that previous question, we were concerned about it cannot be used for which of the following. However, in this particular question, it is about it can be used for which of the following. So all three is the right answer. It can be used for all three of the problems. I mean all three of the following. That is, pressure correction approach can be used for time dependent flows and three dimensional flows and viscous flows. So let us now look at the options given. Option A 1 and 2, option B 2 and 3, option C it is 1 and 3, option D 1, 2 and 3. Since all three statements given are right, we need to go with option D, that is option D, which is like pressure correction approach can be used for time dependent problems, three dimensional problems and viscous problems. So answer is option D. We'll go to question 16. Which of the following is true in incompressible flow? Velocity does not vary. 2. Pressure does not vary. What is incompressible flows? There we say that density variation is not much. So in option A, it is 1 only. Option B, it is 2 only. Option C, it is 1 and 2. Option D, neither 1 nor 2. So here incompressible flow is nothing but where there is no density change, or the density change is very small. But in the statements given, it is mentioned that velocity does not vary. Is it true? It is false, because velocity would be varying from the inlet to the outlet section obviously. But what is important is that the flow velocity should be like within the limits of Mach number less than 0.3. And second one, it is pressure does not vary. Again, it is false, because pressure variation would obviously be there in any system concerning fluid flow, or in most cases pressure variation is what it is governing the fluid flow. So both are false. Like therefore, right answer is 1 is false, 2 is false. C, it is including 1 and 2, which is false. Therefore answer is option D, neither 1 nor 2. Like both are false. So answer is option D. Question 17, it is about which of the following effect poses a special problem in incompressible flows compared to compressible flows. So first one non-linearity, second one coupling, third one evaluation of pressure. I would like to mention here, please read the question carefully whenever you are answering any questions, because a similar question was asked in the previous like few slides back, where the right answer was which of the following like three, all three were there, because the question was about which of the following effect poses problems in incompressible flows. Question stopped there, but in this question there is an extension to the question mentioning that which of the following effects poses special problems in incompressible flows compared to compressible flows. So here the main part is compared to compressible flows. So first one non-linearity, second one coupling, third one evaluation of pressure. So non-linearity is there between, it is a common factor between incompressible flows and compressible flows. Second one coupling, it is also common between incompressible flows and compressible flows, because if you remember the equations, there is a coupling and non-linearity present in both the terms, like in compressible equations as well as incompressible equations. Only difference is that in incompressible fluid flow governing equations, density term would have been taken common, and or it would be like, if it is, but ever evaluation of pressure is there, which is, I think there is an echo, right? Okay, evaluation of pressure is there, which is the problem only for incompressible fluid flow domain, because in compressible fluid flow what we did, we calculated the pressure from the equation of state. Therefore it was not a problem in compressible flows, but in incompressible flows evaluation of pressure is an additional problem. Therefore only third option is right. When it is compared to compressible flows, only third option is right. So looking at the options, option A 1 only, option B 2 only, option C 3 only is the right answer, because even though all three are the problems in incompressible flows, but when compared with the compressible flows, what is excess? Excess is that evaluation of pressure. Have almost 6 more problems, I guess. And that's it. Yeah. Which of the following is true about pressure in incompressible flows? Which of the following is true about pressure in incompressible flows? So first one, it serves to enforce continuity constraint. Second one, it can be specified as a constant. Third one, it is superfluous variable and its evaluation is not necessary. So what is that? Which of the following is true about pressure in incompressible flows? The first one, it serves to enforce continuity constraint. And second, it can be specified as a constant. Third, it is superfluous variable and its evaluation is not necessary. Hmm. It serves to enforce continuity constraint is true. Second one, it is can be specified as a constant. Pressure cannot be specified as a constant because pressure is varying. How can we give that as a constant? So second one is false. Third one, it is superfluous variable and its evaluation is not necessary. Again, it is false because pressure evaluation is very much needed. Because if not, why do we need to go for that? Like if you remember the Navier-Stokes equation, the problem arises because the pressure and velocity both are varying with respect to location. Therefore, it is like coupled equation and therefore the problems arises. That is a different story. But if it is not an important variable, why do we need to go for that much trouble if the evaluation is not necessary? So third statement is false because it is not a superfluous variable and its evaluation is necessary actually. So 2 and 3 statements are wrong and only first statement is right. So looking at the options, we have A1, B1 and 2, C1 and 3, D none of the three options. So and actual answer is option A1 is the right answer. We now go to question. Okay, we have covered week 8 assignment problems. Now we have got week 9 practice problems, like non-graded assignment problems, which we will look at now, and we'll see if like this would be helping you guys in solving the assignment problems for week 9, which the submission is coming Wednesday, I guess. So like it would be helpful in solving the assignment problems. Okay, now we'll go to it. It is mostly about the numerical techniques available for solving the CFT problems. So we have a case here. In that it is mentioned you wish to solve the Poisson equation in a two-dimensional domain spanning a length L in the x direction and width W in the y direction. You have divided the length into 20 equal intervals and width into 30 equal intervals. You have non-zero Dirichlet boundary condition on all sides. You discretize the equation using central difference approximation of second order accuracy. The source term is constant. You wish to solve the resulting set of linear algebraic equations which you have expressed in the form Ax is equal to q. For this problem, answer the following questions. So what are we doing? You wish to solve the Poisson equation we are solving in a two-dimensional domain, and which is spanning length L in the x direction and y in y direction we have W, and divided length into 20 equal intervals. We have divided it into 20 equal intervals, like similar to that. And with W into 30 equal intervals. And yeah, 30 intervals we have. And we have non-zero Dirichlet boundary condition on all sides. What does it mean? If boundary condition is Dirichlet, we have values of variables. So we have variable values in this Dirichlet domain, and all values are non-zero. And discretize the Poisson equation using central difference approximation of second order accuracy. So we are Poisson equation is second order, dou square, like that it will come. Second order derivative, second derivative, and we are discretizing using central difference scheme. So we will be having 5 variables in one equations, if you remember. So and source term is a constant. You wish to solve the resulting set of algebraic equations, and we have expressed it in terms of Ax is equal to q. So A is the domain of interest and x is the variables, and q is some constant resulting from that equations after discretization. So we'll now see the problems. Question 1. Which of the following equations are appropriate governing equation for this problem? First one, dou f by dou t plus a dou f by dou x plus b dou f by dou y is equal to 0, where a b is greater than 0. Dou f by dou t is equal to gamma times dou square f by dou x square plus dou square f by dou y square plus c, where c is greater than 0. And this one, dou square f by dou x square plus dou square f by dou y square is plus d is equal to 0. And this is dou square f by dou x square plus dou square f by dou y square plus e is equal to 0, where both are greater than 0, and here it is greater than 0 and less than 0. Like here it is mentioned that source term is constant, so we are like using a constant values, and it can be greater than or less than 0, and this is like greater than 0 obviously, because dou square f by dou x square plus dou square f by dou y square, it is accounting, so it is greater than 0. So actually speaking, these two are the representation of the Poisson equation. In the question it is mentioned that we are solving for the Poisson equation, therefore option 3 and 4 are right. Option A 1 false, option B 1 and 2 false, option C 4 only. 4 is true but it is not 4 only, therefore right answer is option D, that is 3 and 4. We will see that Poisson equation is an elliptic equation where we have in 3-dimensional form dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square is equal to function of xyz. Here we have mentioned that source term is a constant, so it has become some constant, and it is a two-dimensional problem, so we are having only these two. That is dou square f by dou x square plus dou square f by dou y square. And we are having additional term, and it can be taken this side or that side, whichever side it is the same. So greater than 0 or it is less than 0. It can be that side also. So therefore our answer is option 3 and 4. Poisson equation is an example of hyperbolic equation, parabolic equation, elliptic equation. It is of mixed character. In the previous slide itself we have seen that it is an elliptic equation. So it is like dou square f by dou x square plus dou square f by dou y square is equal to a function of something. And therefore it is an elliptic equation. So answer to this is option C. For an interior point, how many terms involving phi fij will have non-zero coefficient values in the discretized equation? So if it is an interior point, how many equations fij will have? So it is mentioned that we are using second order equation and central difference approach. So if you remember, in central difference we will be having something like this. When we are discretizing dou square f by dou x square and dou square f by dou y square, like it is the equation, and we are discretizing it as with respect to I domain, x domain, I minus 1j, fi plus 1j. This is 1, this is 2, this is 1. Divided by delta x square. This is second order accurate central difference scheme for dou square f by dou x square. Similarly, for dou square f by dou y square, we have fij minus 1 minus 2 times of fij plus fij plus 1 is equal to divided by delta y square is equal to c. So we are having this particular domain over here, and if we look at it, we have 1, 2, 3, 4 and 5 variables. So like interior point, how many terms involving fij we have? We have 5 fij. We'll have non-zero coefficient values. Like all these are non-zero coefficient values only, so we have 5 points. So option A it is 3, option B it is 5, option C it is 7, option D it is none of the above. So right answer is actually option D, that is 5 points is the right answer. Okay, total number of equations to be solved will be around 550, around 600, around 650, around 100. So it was mentioned that we have 20 cells in the x direction and 30 cells in the y direction. So let us now take a simple example. We are having this simple two-dimensional mesh where x direction is divided into 4 and similarly y direction is divided into 4. So how many equations we will be having? We will be having equations for all the central domain. So how many points we have? We have 3 points in the x direction and 3 points in the y direction. 3 points here and 3 points here. And so it is 3 cross 3. So how did we get 3 cross 3? Because we have eliminated 1, that is 4 minus 1 and 4 minus 1. Because on the whole we have 5 points and we are excluding the boundaries. So 5 minus 2. And similarly 20 points if we discretize, we will be having 21 points. 20 cells if we discretize the L into 20 cells, we will be having 20 plus 1 points, and we should neglect the two boundaries. 21 minus 1, it is 19 points. Similarly 30 plus 1 will be having 31 points, and we should neglect 2 points. So it is 29 points. 31 minus 2 is 29. So number of equations to be solved is 29 into 19, 551. Because what are we doing? We are solving 3 cross 3 for this simple domain. Therefore on that basis we are having 29 into 19, we have 551. So around 550 is the right answer. Option A is right answer. Now we have an interesting question. The percentage of elements in coefficient matrix A having non-zero value will be of the order of greater than 99%, less than 0.01%, around 1%, around 50%. So if you remember, we make A matrix into X into Q. This X is nothing but all the points, right? So how many elements will have non-zero coefficients? So it is percentage of elements in matrix A having non-zero value is these many points divided by total number of elements. That is like we have 551 interior points, right? 551 equations to be solved. So x is 551. So A is 551 cross 551 and Q will be 551 again. So in those 551 cross 551 points, these many points are having non-zero values because rest will be having zero values. So on that basis, it is like coming out as 0.8%. So we have options as greater than 99%, less than 0.01%, around 1%, around 50%. So right answer is option C, around 1%, because what answer we were getting is 0.8 percentage. So now let us look at how is that answer. So Poisson equation is nothing but dou square f by dou x square plus dou square f by dou y square, where is my cursor? Yeah, is equal to C. So now we are discretizing using central difference scheme of second order accuracy. Fi minus 1 comma j, Fij minus 2 Fij plus Fi plus 1j divided by delta x square plus Fij minus 1 minus 2 times of f of ij plus Fij plus 1 divided by delta y square. So this is the equation. So for every equations we have 5 discrete points. Okay, now we are clear till that. And the next one, what percentage of elements in matrix A having non-zero value is this. So number of equations to be solved is 551 because we have got 29 into 19 data points and 19 interior points. So for every interior point we will be having one equations. So on the whole we have 551 equations. So Ax is equal to Q. If we write x is 551. So number of data points or number of elements in coefficient matrix A will be 551 cross 551 because it is a square matrix. In this case, it is like 551 cross 551. And interior grid points. Okay, now we need to identify something. This is the boundary. Next to the boundary, we have certain cells which will have limited values, but in the interior points there will be 5 elements present in the boundary. I mean in the cell next to the boundary, some values will be becoming boundary values, so those variables will not be present, those variables will be 0. So we need to find interior grid points. Like interior meaning like inner grid points. So we have that we are eliminating again 2 more grid points, right? The first case we have seen how many are present here, and since we are eliminating the grid points, 2 grid points which are next to the boundary, we are getting 29 minus 2 because we are eliminating one from this side, one from that side. Similarly for y, one from this side, one from that side. 29 minus 2 and into 19 minus 2. We have 459. And this is equal to 459 we have 459 interior grid points. And remember that in the interior points we have 5 variables. Okay, we have 5 variables which are present completely. So 459 into 5 we have 2295. 2295 grid points are present for those, and variables are present in those equations, in those elements. So 2295 variables are present. Now we should come to the bottom and top. In the bottom and top, like here again we are excluding the 4 corners, except the 4 corners we are taking 1 2 3 4 like that. If it is this point we are excluding 1, right? So here we have how many points we'll be having? This 1 point, this 1 point, this 1 point, this 1 point. So for this point, this is a known because it is a boundary. So we have 1, 2, 3, 4 variables. So next to the boundary, like grid points next to the bottom and top wall. Bottom wall, this is next to the boundary layer. Bottom and top wall, and the left and the what is this? Right walls. So in the bottom and top walls, we have 4 points. So it is like 19 minus 2. So like here we have 19 minus 2 points. Like here we have divided into 20. So it is 20 minus 21 minus 1. 20 plus 1, we have 21 grid points minus. Okay, it should be actually speaking 21. This point we are excluding, right? And that point also we are excluding. It will be 20, 19. Yeah, therefore we are subtracting 2. So like we have 19 points and we are excluding the corner points. So we are subtracting again 2. So it is 19 minus 2, and we have 4 variables for those points. So we have 4, and since we are using it for top and the bottom wall, we are multiplying it by 2. So 19 minus 2 number of grid points into 4, those many variables are present in that, and into 2. It is like 4 into 2. We are having 136. And grid points next to the left and right wall. Similar calculation we need to do for the left and right walls. But here the is divided into 30 points. So here it is 30 plus 1, 31 points are there. And we are having 31 minus 2, 29. Again we are excluding corner points. It is 29 minus 2. 29 minus 2 into 4 variables into 2. 216 we are getting. And now we are left with 4 corner points, right? So 4. In those 4 corner points, we have 1. For this particular point, we have 2 variables which are lying in the boundary. So in the proper equation, we need to have 5 variables. So it is like 5 minus 2. We are getting 3, right? So 4 corner points, we have 4 into 3, 12. So we are adding everything over here. 2295 plus 216 plus 136 plus 12. And we are, these many elements are present which are non-zero. And the total elements, what are they? 551 cross 551. So if we add this and subtract that, we are having 0.8%, which is around 1%. It is not exactly 1%. So around 1% is the right answer. So which is given by option C. So percentage of elements in the coefficient matrix A having non-zero values. We have included, we have found out which values will be non-zero, and we have summed up all those variables and divided by the total number of elements in the coefficient matrix A, and we got it as 0.8%, which is around 1%. So the right answer is option C. So that's it for this week's session. If you people have any doubts now, we can discuss now. Yes. So if there are no doubts, we can close the session. Or if there are any doubts, we can discuss now. That's it for today's session. But like we can, I hope it is clear. Today we have seen about the solution of the Navier-Stokes equation for incompressible fluid flow problem, and solution of linear algebraic equations. Basic methods we have seen, like number of equations, number of variables, all those stuff we have seen. I hope with the practice problem solution you will be able to solve for the assignment for the week 9, and we can again meet next week at the same time. Hmm, from 3 p.m. to 5 p.m. on Saturday. If there are any changes, it will be intimated to you priorly. Uh, Unless otherwise specified, intimated to you priorly. So yeah, thank you guys for attending. If there are any problems in this session, please let me know. Like, it would be better if you can put it in the comments in the YouTube video, so I can just reply easily, or else we can see in the NPTEL website also. Uh, Anything is fine, but I think no one is there to ask questions, so I just close the session. I thank again for attending the session, and we'll meet again next week. Thank you guys. Yeah.